Cool. So it turns out there's a power outage somewhere near campus. So we've got a couple people who are not able to join because of that. So probably a few more are watching sort of asynchronously than necessary. So first homework's due Monday, of course. The TA office hours are this afternoon. I want to say I'm, available for email help and stuff over the weekend, right? But if you email me at 8 o'clock on Sunday night, don't necessarily expect a response before Monday morning, right? And I think the same goes, for the TAs. We're happy to help, but please be respectful of our time as well. This weekend, I should finally be able to get these mastery questions sorted out. And the issue is there's a third-party Carmen plugin that is really good for these sorts of things, but it's not at all intuitive or easy to use. And there's like a whole sort of like programming language you have to learn to be able to write these questions that can take numerical answers and things like that. So I haven't quite been able to make it glitch free yet. I've also received a bunch of emails regarding the reading quiz where people felt that they got slighted on one of the questions because I picked one of the two correct answers, or some disagreement about whether one of the things I said was a correct answer was actually true. Again, the purpose of this is just to make sure that you've actually read it, right? So I'm just going to make sure that everyone who took the quiz gets full points for that question. I really don't care. I'm not out to screw anyone. And if you're taking umbrage with the way Carmen graded you, that means obviously you did read it because you know what's what's happening, and that's all I really care about. Okay, so we're done with sort of the equilibrium thermodynamics portion. We looked at the review, and then we had the looked at stability of heterogeneous systems and looked at the Gibbs free energy and showed how that predicts what's going to be the equilibrium composition. And then with polymers, we looked at spinodal. So we looked at the separation to metastable components. We're going to look at spinodal decomposition more quantitatively when we talk about diffusion and diffusional phase transformations. But now we're into the non-equilibrium world, right? And this is solidification, right? Topic that's super important for lots of materials processing, obviously metals, but also the same things that we're talking about for solidification here also talk about vapor processing. So physical and chemical vapor deposition, PVD and CVD processes. So most of what we're talking about here for solidification also applies to this, especially with nucleation of solid phases from either liquids, melts, or vapors, right? So, and of course, solidification is super important for all the welding engineers in the class. So, okay, so this is the picture that we have from classical thermodynamics, right? From the equilibrium picture. We cool down until we hit the equilibrium melting temperature, right? And then the temperature is constant as the latent heat of essentially fusion kicks in, and we are forming a solid from the liquid until we've completely frozen, and then we start cooling again, right? But this picture is completely and totally wrong in practice, right? Because this assumes that we're freezing in a reversible manner, right? But there's actually no driving force for solidification if we're right at this temperature, right? This is a good model, right? And if we're doing calculations of what the phases are and things like that, it actually works really well. But to get an actual picture of the process, right? So for the homework assignments in the thermo review, right, I ask about what are the states of the alumina thermite reaction, right? This is a perfectly good model to use for that. But if we're considering what actually happens during the solidification process, we actually have a region of undercooling, right? And again, there's no driving force for solidification at this equilibrium temperature, right? And we have to nucleate, right? We have to create a little region of solid from our liquid. So that means we have to go below our equilibrium temperature, right? Then we're going to have heat evolved by the late of fusion. It's going to go back up to this melting temperature. And this can be pretty dramatic. This can be really dramatic. I once saw a fantastic demonstration of homogeneous nucleation in cooling in nickel, right? Where they had a really essentially clean amorphous quartz crucible and an alloy that was right at the eutectic temperature. So, you know, the lowest, the eutectic composition, so at the lowest melting point. Essentially it was in an induction furnace, so everything was able to stay nice and cool. You had red hot liquid, well, like white hot liquid, come down through the cooling temperature and actually got an undercooling of about 200 degrees, when all of a sudden it instantaneously froze and the temperature shot back up to the melting temperature when it completely solid. So they were able to get what in the solidification world is called an undercooling of 1, right? That you were able to undercool sufficiently that you could freeze out all of your metal instantaneously, and this latent heat that evolves doesn't leave some melting. So this pop-up in temperature here is called recoalescence, right? But this is the picture we want to keep in mind. So now the critical question is how much of an undercooling can you get before the solid actually nucleates, right? And what's the theory that's going to determine what goes into understanding where this undercooling comes from, right? And we do have to remind ourselves, right, that alloys and mixtures don't have a set melting point, right? They're going to, or solidification point, they're going to freeze out over a range of temperatures, right? And that the composition of the newly formed solid is going to change as we go through this freezing zone. Okay, so let's start. Today we're going to talk about homogeneous nucleation for solidification. On Monday, we'll get into heterogeneous nucleation, and then solidification of alloys and chemistry. So for right now, we're just going to assume we have a pure metal, or a pure, it really doesn't matter, a pure material of any sort. Okay. So what solidification is and melting is, we all know this. This is a transformation, a phase transformation between a crystallographic and non-crystallographic state of a material, right? So we're not talking about the melting or the softening of amorphous material, right? So coming down and going from a liquid glass to a solid glass is the vitrification process, and that's fundamentally different on a couple different levels than solidification of a crystal. And so we're going to talk about vitrification later. Oh, where's the arrow? So when we cool a liquid below its equilibrium melting temperature, we now have a driving force for solidification. Exactly at the melting temperature, right, there is no driving force for solidification, right? You need to, the free energy of the liquid phase and the solid phase are exactly equal, right? So both are perfectly happy to sit there in equilibrium with each other, right? So we need a little bit of undercooling for solidification. We can reach pretty sizable undercoolings in pure and highly clean systems, right? And that's simply because of nucleation, right? The transformation has to begin by the formation of these very small solid particles or nuclei, right? Okay, so under most conditions, nuclei are relatively easy to form at container walls or other impurities in our system, right? So most of the time we have heterogeneous nucleation, right? Anytime we have other crystals in there, if we have oxides or carbides or other phases that don't completely melt, tiny little specks of dirt, if we have a mold wall that's crystalline, we can get heterogeneous nucleation much easier than the homogeneous theory we're going to talk about today, right? But the homogeneous nucleation is really important from a fundamental understanding of the physics behind solidification. Okay. So what do I mean by homogeneous nucleation? Well, we've got a liquid, and we can pretend that this liquid is essentially infinite in extent. And somewhere in the middle of that liquid, we're going to form a tiny little particle of solid, right? And so we have to start with our temperature is below our melting temperature, right? So we're in the range, and in the complete liquid, we have the Gibbs free energy here. That's just the volume of the liquid times the volumetric Gibbs free energy of the liquid, right? So some of these ions, atoms, molecules, depending on our material, right, they're all going to cluster together to form a small sphere of solid. And the free energy of the system is going to be, we have the volume of the liquid times the Gibbs free energy of the liquid, the volume of the solid times the Gibbs free energy of the solid, plus we have the interfacial energy of the solid-liquid interface times the surface area here, right? So if we look at the change in the free energy of the system is very large compared to the volume of the nuclei, right? So we can ignore, we say basically that the Gibbs free energy of the liquid component basically stays the same, right? So our change in Gibbs free energy is given by the solid and the surface energy component, right? And this delta GV, this volumetric Gibbs free energy, right? We know from our thermo review that's given by the latent heat times our undercooling divided by the melting temperature here, right? So there's nothing surprising here, just sort of basic thermodynamics. Okay. We can put everything together and essentially we come up with this figure, right? And this is one of these really important figures because this is exactly the same figure with a very minor change for elastic effects for nucleation of solid-solid for diffusional phase transformation, right? So what we have here is two components to the overall Gibbs free energy of the system. The first is the interfacial energy, right? And the interfacial energy is going to be proportional to the surface area of the sphere, right? So that's going to be proportional to the radius squared. And then we have the volume component, which is going to be proportional to the radius cubed of our nucleus times our temperature, undercooling, right? And notice the interfacial energy is essentially temperature independent. For right now, we can assume that. And what happens is this, our squared component takes off first, right? So it has a greater initial slope. So at small particles, we have a positive delta G, right? But then this volumetric term, this bulk free energy term quickly catches up. So we pass through a maxima and then decrease. So if we look at this, the free energy is a function of the radius of our nuclei. We really clearly see we need a radius large, a nuclei with a radius larger than this R star value in order for the nuclei to be stable. If we're at a size that's smaller, this system can reduce the free energy by just dissolving away the nuclei, right? So we need to create a nuclei that's just slightly larger than R star. Then the system will reduce the free energy by the nuclei growing, right? And so this is a really, really important picture, right? This is just one of those figures like the common tangent construction that's crucial to understanding of this class, right? And this is just something that you happen to know really well. So this figure as it's drawn is for one particular value of delta T, one particular undercooling. What happens as we increase or decrease the undercooling, right? If we increase the undercooling, meaning that we're at a temperature much lower, right? We're increasing the distance from our melting temperature, right? So we're getting colder. Some people always sort of screw that up and say an increased undercooling means an increased temperature, but it's not. An increased undercooling means a decrease in temperature. So what's going to happen? Well, the interfacial energy line is going to stay the same. right? The volumetric free energy has this delta T term in it, so it's going to move this way, right? And as our volumetric free energy curves moves down and to the left, what happens to our R star value? It's going to move to the left, and this hump, our activation energy, or delta G star, is going to decrease. So as our undercooling gets greater, we need to nucleate a smaller radius for it to a smaller nuclei for it to be stable, and the activation barrier that we have to overcome to do that becomes less. As we decrease the undercooling, we move this curve to the right and up, so R star shifts to greater radii, and our activation energy hump also gets higher, right? So this picture sort of explains really well why we need a sizable undercooling sometimes to nucleate things homogeneously. If the interfacial energy between the solid and liquid is fairly high, we have a really high activation barrier, right? This is something that should be intuitive from our discussion of the Gibbs-Thompson effect, right? So if you are one of the lucky few who really groks thermo and was able to sort of internalize the meaning of the Gibbs-Thompson effect, this is basically what we see here, right? When we have a small nuclei, we have a very tight radius, and we have a very high surface area to volume ratio. And so that means the Gibbs free energy of our solid is increased relative to that of our surrounding liquid, right? And that increase in Gibbs free energy is exactly the same as this activation barrier for nucleation. So this, what we're seeing here, is just another way of stating the Gibbs-Thompson effect that we talked about before, right? Or the effect of interfaces on stability, okay? So we can go through the algebra here, right? Right, this R star and delta G star happens at the maxima of this curve, right? So it's the critical point of this delta G star curve. So we can just write out, or this delta G as a function of radius curve. So we can just take the derivative of this expression, set it equal to 0, and solve for what R star should be, right? And we can go through that, and what we see is this delta G. We get this expression for delta G star, and this expression for R star. So we see that the critical value of radius for nucleation has the surface energy term, the change in the volumetric free energy, and this again is exactly what we got from Gibbs-Thompson, right? So it all, thermodynamics all holds together, which is a really good thing. We're consistent at least, right? So the activation energy, if we look at it, we have a term. Well, let's do a little algebra and sub things back into here. And so we can see here that the activation energy for nucleation is going to depend on, primarily here we see the surface energy cubed, right? So small changes in surface energy give us a really dramatic change in the activation energy that we need to come by, right? So if we can reduce the surface energy, right, through heterogeneous nucleation, right? So if we have a surface, if we have something in our liquid where the interfacial energy between that something and the solid is much less than the interfacial energy between the solid and the liquid, basically meaning any other solid in our system. Our activation barrier for nucleation is going to be really, really reduced, and heterogeneous nucleation is going to occur, right? It's also going to be the delta G star is inversely proportional to our undercooling squared, right? So the greater our undercooling, we really reduce this activation energy as well, right? And then there's some minor things that go in there, like the melting temperature and our latent heat, right? But the primary contributions are our surface area and our undercooling. Okay. Okay. So let's. I want to play a game here really fast. So I've got two sets of randomly generated particles, okay? The question I'm asking is which one is actually uniformly random and which one has stronger particle interactions, right? Whoa. So everyone sort of hop in here. Give a couple seconds here.
Question.
Yeah.
Question on the top hat was different than the question on the slide.
Wait, are we supposed to answer this in top hat or just the poll?
Just the poll on Zoom. Right, so which one is uniform random? And which one has strong particle interactions? Okay, so we got a good chunk of the class answered. So I'll share those with everybody, right? So it's actually fairly evenly split, which is good. I was also slightly unfair with the way I worded the question, right? Because I said which is random and which has stronger particle interactions. It turns out that, you know, the one on the left is actually uniform random, right? So you guys probably have a bit of advantage, right? Having a science and math background, but most people have a really bad sense of what randomness actually is, right? The one on the right is actually created from a model of certain glowworms in a cave, right? So these are insects that glow. So if this was taken by, you take a picture of the wall, and you can see that they naturally spread out, right? Because they're all competing with resources. Mm-hmm. So there's actually a slight repulsive interaction between the particles in this picture, right? Whereas if most of you said this is closer to random, right? I'd like to think it's because you had a good statistics project in Mod Sim last year. With Dr. Bowie. But in general, humans are really bad at identifying randomness. So what does this have to do with anything? Well, if we assume that the particles in the liquid are actually sort of hard spheres that don't have much interaction, right? Kind of like an ideal gas model, which is actually not too bad of an assumption. You can naturally see that we get clusters, right? We get these types of clusters, right? And these are like the little clusters that can form into nuclei, right? If the liquid was like this and everything was sort of spread out and sort of what appeared to be more uniformly spread out, we would never actually get any nucleation, right? Forming these clusters would be much, much more difficult. Okay? So the statistics behind this is actually the Boltzmann or the Gibbs, or sometimes called the Boltzmann-Gibbs distribution. And this is different than the Maxwell-Boltzmann distribution that you learned about in physics, right? So the Maxwell-Boltzmann distribution gives the energy, the speed, the distribution of speed or momentum of gases as a function of temperature, right? This is a fundamentally different distribution, but also developed by Boltzmann in the mid 1860s, and then it was applied and further developed by Gibbs in 1902. And the Boltzmann distribution really forms the link between microscopic and the macroscopic formulation of entropy. It allows you to go from configurations to macroscopic probabilities, right? And it basically says here that the probability of finding your system in state I with some energy epsilon I is given by this expression, right? So 1 over a normalization constant z, and then it's e to the minus epsilon energy over kt, right? So what is z? Z you probably touched on in thermodynamics, right? This is the canonical partition function that details all of the states that a it tells you the different energies for all of the different states for a thermodynamic ensemble, right? I don't want to get into the statistical mechanics of it, but it turns out it isn't needed, because we really don't care about the absolute probability of one state. What we care about is the change in probability of states that comes about when we have a change in energy, right? So we can do this ratio, and the canonical partition function gets canceled out, where we have a 1 over z in both the numerator and the denominator. And we end up with what we have here as called the Boltzmann factor, right? Where we can say the probability of state I is equal to the probability of some reference state, right? Typically what we do is we take the average state of our system because we know the energy for that exactly. And then we can calculate, well, what's the change in energy from our reference state to the state we're actually interested in, or our delta change in energy. And then we can get a probability out here, right? So this is our Boltzmann factor that comes from our Boltzmann distribution. And we'll use this sort of, you see this over and over again when we talk about changes in energy of our material, right? So this is not explicitly talked about in the reading, but it's so fundamental behind everything. I think it was really a shame that it was left out. So I wanted to just throw it into the lecture at least, right? So where do these clusters come from? We showed the example of randomness and showed that if we have actual random interactions, we of course have lots of clusters. So the question is then, what are the size of the clusters that we expect statistically, right? Can we form an arbitrarily large cluster at a given temperature? And you can guess that the answer to that is no. Otherwise, we wouldn't have the need for undercooling, right? Because a sufficiently large cluster would just naturally be there in our solid. Okay, so our liquid volume here is about 2 to 4% larger than that of the solid. We do have slightly more freedom of movement in the liquid than in the solid, right? But we have to also keep in mind that our local structure in the liquid is fairly similar to that of the solid, right? So if we look at these atoms in the liquid, these less dense regions, you know, they still take the same general approximate close packed form, even in this exaggerated figure, right? There's just a greater free volume in the liquid relative to that of the crystalline solid, right? And we have random thermal fluctuations. All these atoms are going to be vibrating. So what we really want to ask is, what is the probability of random vibrations bringing together clusters of sufficient size that they can grow into a stable nucleus? Okay. So the liquid contains many of these small close packed structures, right? We can use our Boltzmann distribution to determine the number of spherical clusters of a given radius, right? Okay, so this has a number here for the radius, right? How is that related to the probability that we have before? Well, the number of clusters divided by the total number of atoms gives us a probability, right? So if n naught is our number of atoms, nr divided by n naught is our probability of finding a cluster of, probability of finding a cluster of size r. We should have the probability of the reference state here. But if we're taking our reference state as an individual atom, not being clustered at all, this just becomes n naught divided by n naught, or 1, right? So this is just the Boltzmann distribution hidden in a slightly different form by normalizing it, by a clever choice of the reference value. Okay? So what we want to determine is if nucleation is going to occur, we need to compare the expected size of the cluster against R star, right? So we can figure out the temperature here where we have at least one cluster larger than R star, right? We don't need a lot of these. But it turns out, because this is exponential, this NR is essentially 0, 0, 0, 0, and then it takes off really, really fast. We'll see that in a couple minutes, right? So for homework, one of the problems that you're going to have is to show that we get where we start to see an appreciable number of nuclei is when our delta G star is less than or about 78 KT.
Escalate.
Does someone have a question?
Symbiosis. Symbiosis.
Okay. I keep forgetting to mute. Participants. Mute all. Okay. There we go. I should just keep that window open. Okay, so we can illustrate this graphically, right? So we showed how R star decreases with increasing undercooling, right? And we can calculate what is the maximum size of the clusters in our liquid given the undercooling that we have, given the temperature, what's the greatest cluster that we have. And that increases exponentially, R star decreases exponentially. Where they meet is actually our nucleation temperature. So delta Tn is the maximum undercooling that we can get for homogeneous nucleation, right? And notice delta GR, right, has a different dependence on the, well, they have, I was going to say something. I almost said something incorrectly. Right, but notice they have the same dependence on the surface energy as R star, right? So we end up with sort of similar type exponential rates, but one decreasing and one increasing, right? So we can look at the nucleation rate now. So let's pretend we get to this critical nucleation temperature where we now have a cluster. We are now forming clusters that are the same size as our critical nucleation, right? So how fast are we going to actually, how many nuclei per second are we going to form? So at our critical nucleation temperature, we can see that there's this n sub R star number of clusters of size R star, okay? So it turns out that this density of clusters is about 10 to the 29th atoms per cubic meter for most metals and things of similar density, which seems like a lot, right? But you got to remember, a cubic meter is huge. Right, is an absolutely staggering number of atoms, right? So if you figure out the actual fraction of the atoms, it's very, very, very small, right? So if you take a small amount of liquid, you have to really get to your critical undercooling before you have any the chance of having any clusters of R starred in there. Yes, yeah, you're right. This should be clusters per meter cubed. Okay, and we have to also remember that due to this exponential nature of the Boltzmann distribution, it means that there are effectively 0 clusters bigger than R star. So if we take the number of clusters that are R star plus some finite delta, that's equal to 0, right? And these clusters of R star are not yet stable, right? They're right at the cusp of being stable. But if one atom leaves the cluster, they're going to dissolve. If one atom joins the cluster, then they're going to become a stable nuclei and grow. Yeah, shoot. Okay. Thanks for pointing that out. Yes, this should be clusters per meter cubed, or clusters. Yeah, not right here. This says clusters meter, or meter clusters. So just correct that real fast. Okay, so how often are these critical clusters going to transform into nuclei, right? So what determines how often atoms can join or leave a cluster, right? So again, we're not going to get into the actual particle physics of it, right? But it's going to depend on the vibrational frequency of the atoms, right? Which is, of course, temperature dependent. The activation energy for diffusion of a liquid, which is also temperature dependent. the surface area of the cluster, right? The clusters themselves are not perfect spheres. We model them as perfect spheres, but in reality, they have to take some kind of shape based on the anisotropic energies associated with bonding, right? So in a metal, a sphere is not a bad assumption, but in an ionic or covalent system where you have strong directional interactions, you're highly unlikely to make a spherical nuclei. But anyway, the frequency of attempts ends up being a complicated function, but it turns out it's about 10 to the 11th per second, right? Which is fairly similar to the vibrational frequency of the atoms, right? And when I say fairly similar, I mean within an order of magnitude or two. So the number of conversions is essentially saying the number of clusters times this frequency of attempts, right? So what does this actually imply? Okay, this is the law of the statistics of large numbers, okay? The probability of you winning the lottery is vanishingly small, right? Picking 6 numbers out of all the possible combinations is a vanishingly small chance, right? That your ticket is going to win, right? What's the probability that some ticket wins? Is essentially 1, right? If you sell enough tickets, the probability that someone has a winning ticket approaches 1. The probability that your ticket is the winning ticket approaches 0, right? So here what we have is the probability that any atom is in a cluster that forms a nuclei is vanishingly small, right? But given the number of attempts that occur per second, you're guaranteed that somewhere in your solid, you're going to get this occurring, right? So it gets really weird when you think about the statistics of large numbers, right? So if you look at it, it's virtually guaranteed that out there, someone has won the $1 million lottery jackpot twice, right? And there are numbers of winners, right? But those are such rare events, right? You know, the other way of thinking about it is 1 million seconds is not really long, right? Could a resonant frequency be used to break up these clusters? Yes, but the frequency is really, really high. But there has been things related that people have done with like ion traps and things like that, where they use laser light frequency to keep things from coming together. So you could keep individual ions suspended and keeping them from forming forming compounds and things. But the theoretical physics there is a little beyond my pay grade, right? So what's Nate saying? The probability that your ticket wins remains constant. Yeah, so essentially yeah, the probability that your ticket wins remains the same, right? No matter how many people go in, right? And the odds of you winning is still astronomically small, right? So, right. So for those of you listening asynchronously, those are questions that came through in the chat. Okay, so if we put this in, how sensitive to temperature is the nucleation rate? And it's very, right? So essentially, it's a step function. At below the critical undercooling, we have no nuclei. And then once we hit there, we shoot up, right? So it's like the Heaviside step function, right? It's just an impulse. Nothing happens, nothing happens, boom, tons of nuclei, and we instantly freeze out, right? And so this is the weirdness that happens when you have these probabilities that depend on exponentials, right? And we have two of them together, right? The gap between R max and R star is very, very large up until they meet, right? They come together very, very steeply, right? And we end up with this step function for the number of nuclei as a function per second as a function of temperature, or the nucleation rate as a function of temperature. Okay. And so we'll stop there. On Monday, I want to talk about some really nice experiments done in the late 40s, early 50s by David Turnbull, exploring homogeneous nucleation. And we'll also get started with heterogeneous nucleation and growth of solids on Monday. Have a good weekend, everybody. So a video of solid to liquid nucleation, it happens really too fast to capture. At least I'm not aware. I'll take a look. But solid nucleation, we can do things. And there are, if you want a video of a simulation, right, there is like molecular dynamics simulations of nucleation that happen on the correct time scale, right? So the picosecond type time scales that these individual vibration, these clusters come together on. Okay. Shoot. Well, guess what I get to do tomorrow morning? I get to re-record this because I get to redo this because I forgot to hit record. Oh man.
It says you're recording on my screen.
It does?
It does, yes.
Hallelujah, I'm saved. Oh, I thought I'd have to give this lecture a second time. Normally, I have a little flashing sign that says recording. But I guess I must have accidentally closed it. Okay, well, have a good weekend, everybody. And we'll see you Monday.